The history of physical science is usually told as a strictly Western triumph. Things like advanced metallurgy or rust-proof iron are credited to modern industrialization. Yet structures like the Iron Pillar of Delhi have stood in the open air for over 1,600 years without rusting. When researchers look at ancient Sanskrit texts describing complex gear systems, aerodynamic flying machines, and electrical phenomena, traditional historians routinely dismiss them. They are categorized as religious allegories, or simply myths. A new wave of researchers is bypassing that historical debate entirely. Instead of arguing over translations in a library, they are taking these ancient claims and subjecting them to rigorous testing inside modern laboratories. They are deploying three specific methodologies. Chemists are reconstructing metallurgical formulas, engineers are building mathematical circuit models, and geographers are using GIS spatial mapping to test ancient logistical data. By moving these texts from history departments to the lab table, scientists are treating them as empirical engineering data, and they are finding that the math actually works. Testing the Vimana Shastra required translating archaic ingredients using Ayurvedic dictionaries to find chemical equivalents. As shown on this chart, this yielded the lead alloy Tamogarbha Loha. When synthesized, laboratory tests confirmed its unique capability, absorbing exactly 79% of incident red ruby laser light. They didn't stop there. The team synthesized a second recipe, producing a unique copper alloy. Microstructure analysis proved it was highly malleable, and immersion tests showed it is completely corrosion-resistant to salt water. The text also contained mechanical blueprints. Engineers took the specifications for a device called the Vakra Prasarana Yantra and physically built it. The result is a fully functional mechanism featuring 16 interlocking gears arranged in a complex conical formation designed to manage multiple rotational outputs. When researchers cross-referenced the properties of these recreated alloys against modern ASM reference manuals, they found no matches. These ancient engineers invented materials that are entirely unknown to modern science, making them fully patentable today. To audit the claims of ancient electrical generation, we have to look at the baseline logic established in the early 19th century. Pioneers like Dalvani and Volta proved that pairing copper and zinc electrodes in an acidic liquid creates a functional battery. Applying this electrochemical logic to indigenous Indian agriculture yields measurable results. Local fruits with high acidity, such as the mango or Mangifera indica, function perfectly as natural liquid electrolytes when connected to two different metals. To test these organic power sources, researchers wire the fruit into an RLC series circuit containing a resistor, inductor, and capacitor. Applying Kirchhoff's second law to the fruit's voltage, they calculate the exact electrical current. The result? The mango produced a highly consistent electrical yield. These mathematical proofs confirm that ancient societies didn't need modern manufacturing to harness electricity. They had immediate access to the necessary organic electrochemistry to create functional, closed-loop electrical circuits. Zooming out from laboratory tables to the macrogeography of India's coastline, physical archaeological ruins reveal an immense scale of ancient logistical operations. Using GIS and bathymetric models, a spatial map traces massive ancient maritime trade routes connecting India to the Red Sea and Southeast Asia. Overlaying wind vector data reveals a clear pattern. Voyages matched strict seasonal sailing windows, proving navigators possessed sophisticated predictive weather models. Navigating these grueling, wind-driven voyages required structural innovation. Shipbuilders systematically evolved their designs, shifting from fragile sewn plank hulls to highly durable mortise and tenon construction. Ancient India's position as the central hub of early globalized trade was not an accident of geography. It was the direct result of mastering complex environmental data and applying it to structural engineering. Western history frames ancient India as a spiritual society, focused on philosophy rather than physical sciences. But artifacts like the bronze Nataraja illustrate a fusion of ideology with highly advanced metallurgical casting. Decoding these ancient scientific practices is no longer an academic exercise in historical vindication. It has become active, lucrative, modern research and development. Based on translations of these ancient texts, modern scientists are securing patents for new fireproofing sprays, hunger-suppressing nutritional substitutes, and highly specialized industrial alloys. By removing the debate from the library and moving it to the laboratory, empirical testing neutralizes historical skepticism. The sheer scientific weight of these forgotten texts speaks for itself. Rather than constantly looking forward, we're finding that the most advanced engineering blueprints for our future may actually require us to decode our past.